our sponsors, and I'm going to ask you a few questions and you can answer them to get them. But before I begin, let me lay out a few instructions. Please do not prompt the answer from the crowd. If you know the answer, raise your hands and I will pick you. We begin with an easy question. Which edition of Techfest is Techfest 2012? Yes. And you get a mouse for that. No, you get your phone, sorry. Please do not prompt the answer from the crowd. The next time this happens, the question is invalid and that freebie goes to a random person. Or maybe to the organizers. Okay, second question. What is cryonics? Yes, that's it. Yeah.
It is the study of cryonics. That's the technique of preserving human bodies after their death. Destroying them later.
Can you please be a little louder so that everybody can hear you?
So, cryonics is.
Please remain silent. He knows the answer. He's trying to say it.
So you preserve dead human bodies by cooling them down to low temperatures, and so that you can perhaps revive them later after certain years if the medical community has advanced enough.
Yes, that is correct. And you too get your phone. Thank you. We go on to the next question. Futurama and the last airbender had something in common. Something related to this lecture today. And the common thing is? Yes?
What's the question?
Okay, just a minute. Futurama and the last airbender had something in common. Something related to this lecture. What is the common thing? Yes, Yuvraj.
Basically, they were preserved for a long period of time in ice or in low temperature.
Yes, that is correct. Yeah. And you get a keyboard. That was the trickiest question for the day. Okay. We go on with the next question. What is gerontology? What is gerontology? Yes. Yes. It is the study of aging. You get headphones for this. Okay. We have the last question for today. What was Aubrey De Grey before he was a gerontologist? Yes. Yes, sir. Okay, did everybody get the answer? Okay, somebody else in the crowd? Yes.
He was a computer engineer.
Yeah, that's right. He was a computer engineer. You're an RD.
Come on. Get on the track.
Ladies and gentlemen, welcome to day 2 of Techfest. Before we begin this lecture, may I ask you to switch off your mobile phones or put them in silent mode? Flash photography is not permitted, and kindly also do not leave the lecture before it ends. Dr. Aubrey De Grey is a biomedical gerontologist based in Cambridge, United Kingdom, and is the Chief Science Officer of the SENS Foundation, a California-based charity dedicated to combating age process. He is also the editor-in-chief of Rejuvenation Research, the world's highest impact peer-reviewed journal focused on intervention in aging. His original field was computer science, and he did research in private sector for 6 years in the area of software verification before switching to biogerontology in the mid-1990s. His research interests encompass the characterization of all the accumulating and eventually pathogenic molecular and cellular side effects of metabolism that constitute mammalian aging and the design of interventions to repair and or ablviate the damage. He has developed a possibly comprehensive plan for such repair, termed Strategies for Engineered Negligible Senescence, SENS, which breaks aging down into 7 major classes of damage and identifies detailed approaches to addressing each one. Dr. De Grey is a fellow of both the Gerontological Society of America and the American Aging Association and sits on the editorial and scientific advisory boards of numerous journals and organizations. Techfest is proud to present Dr. Aubrey De Grey. Welcome, sir. May I ask one of the organizers to begin on stage?
Oh, thank you. I'm not sure if that's how they do things in India, but that's how they do things where I come from. Right then, well, so thank you so much for coming. I'm delighted to see that the room is so full. I know that most of you here are not biologists, so I will not get too technical, not for most of the talk anyway, but I know also that when I discuss this sort of material with engineers, mathematicians, computer scientists, physicists and so on, I usually get a very good reception, so I'm very much looking forward to this. I also would like to say that this is my first time in India, and I'm really enjoying how well I'm being treated. I think you're all wonderful people. You're treating me wonderfully. Okay, so this is the title of my talk, Combating Aging with Regenerative Medicine. And I'm going to start by telling you a little bit about aging. A lot of people have a very important and profound misconception about what aging is and about what dying from aging is. So when I say I'm combating aging, a lot of people will think, well, hang on, that sounds like a bad thing to be doing. Because they'll say, surely aging is the sort of thing that we want to die of. Aging is what you die of when you escape all of the horrible diseases of old age that we all don't want to get. Things like Alzheimer's disease and cancer and cardiovascular disease and so on. And if you escape all of those, and then you live maybe a nice long time, maybe up to 90, and then you die peacefully in your sleep, and that's all very wonderful. That's the way people would like to go. But that is a biologically incorrect definition of dying from aging. Because the fact is, all of the diseases of old age, the ones I just listed and all the others, are diseases of old age because there must be late stage aspects of some process that goes on throughout life. Otherwise, they would happen to young adults as well, right? And they don't. So, if we combat aging, which is of course that process that goes on throughout life and eventually causes those diseases late in life, then what we are doing is really just preventative medicine against the diseases of old age. That's all that this is about. And if we remember that, and I'll be coming back to that once or twice during the talk, if we remember that, then first of all, let's think about how many people it affects. You can do these calculations. You can say, well, okay, what causes of death are there in the world? How many people die of this? How many people die of that? And you can classify those causes into ones that mainly affect old people and ones that don't, that affect everyone equally. And if you do that, then these are the numbers you get. About 100,000 people a day die of aging. That's about 2/3 of all deaths. That's about the number of people that die total in the world every day. Of course, in the industrialized world, it's more than that because not many people die of, malaria and so on. And of course, in India, a country that's becoming more industrialized all the time and more educated and economically more prosperous, this number, 2/3, is going up. I don't think you're up around 90% yet, but you will be pretty soon. So that's pretty bad news. Plus also, let's face it, what part of this is hard to understand? Even if you do escape the diseases of old age, it's still not much fun getting into this state for a while before you die. Most people would prefer to be this person on the left, even if he is about to have his head bitten off by a shark. So that's why I work in this area. And it's why I have created this foundation, which you just heard about, based in California. It's a charity that where we work on applying regenerative medicine to aging. I'm going to be explaining in a little bit more detail what I mean by that in a moment. But that's what we do. We're interested in combating aging. So what is regenerative spinal cord trauma? Something like that. But it's much broader than that. First of all, the repair can be to damage that accumulated gradually over time. Like aging, for example, rather than something caused by an injury. Secondly, the type of repair can be at the level of replacing whole organs, which is what tissue engineering is, or it could be at the level of replacing cells so as to repair an organ. That's what stem cell therapy is. But equally, we could go down another level of scale, and we could repair cells by replacing or restoring the internal structure of those cells at the molecular level. For that matter, we could do the same thing for the molecules that exist outside in the spaces between our cells. And I'll be coming back to all of those things because they turn out to be very important when we think about applying regenerative medicine to aging. All right, now, what is aging? Well, I've already told you a bit about what death from aging is, but let's give a mechanistic definition of aging, because that's going to be very useful when we try to orient our thoughts around what to do about aging medically. And there are lots and lots of definitions of aging out there, but this one's pretty good for that purpose, for orienting our thoughts, so I like it. Here I'm saying two important things. First of all, I'm saying something which is obvious, something you already know, but nevertheless it must be said in any definition. I'm saying that, well, essentially in colloquial terms, I'm saying that aging is a side effect of being alive in the first place. So what that means is that metabolism, which is the word that biologists use to denote all of the processes that go on in our bodies to keep us alive, eventually causes pathology, which is the word I'm going to use to encompass all of the diseases and disabilities of old age. The diseases I mentioned earlier, also things that we don't necessarily call diseases, like decline in function of the immune system or gain of fat mass, things like that. So metabolism eventually causes pathology. That's the first thing I'm saying in this definition. The second thing I'm saying, which is perhaps less obvious, but very, very important, is I'm introducing this word damage. And I'm going to be using this word damage in this very particular, precise way for this talk. So I want you to be absolutely sure that you understand what I'm going to say here. It's very, very important. Damage consists of the set of intermediates between metabolism and pathology. So in other words, it is the mechanism by which metabolism causes pathology. We have to have something out there that says how metabolism causes pathology, and damage is how it does it. Damage is the set of ongoing, lifelong molecular and cellular changes that metabolism creates, starting even before we're born. But the key thing about damage is that it accumulates. So it's progressive. The progressive changes at the molecular and cellular level happen in our bodies throughout life. And for a long, long time, those changes are harmless because metabolism is set up to cope with them at a low level. But eventually they accumulate to a high level which metabolism is not set up to tolerate, and that's when the diseases of old age emerge and start to progress. So this is the definition of aging that I'm going to be using today. Why is that definition so useful? Well, I'm going to start here in explaining why. Here is the definition I just gave: metabolism causes damage, causes pathology. And one thing we can do is we can distinguish very clearly the two major schools of thought, the two major themes that exist today when people think about the combating of aging with medicine. I'm going to call those two approaches the Gerontology Approach and the Geriatric Approach. All right, now the Geriatric Approach is basically everything that we have today in terms of actual medicine for the problems of old age. And the way I'm going to define the geriatric approach is that it consists of treating those diseases just in the same way that we would treat other diseases of the sort that young adults would get. In other words, we characterize the symptoms and perhaps a little bit about the mechanism, and we try to knock back the disease and more or less eliminate it from the body. But of course that's impossible for aging, because aging is the side effect of being alive in the first place. So we're never going to develop a treatment that creates a non-aging human being. So, in some sense, it's a bit misguided, but in particular, it's quixotic. It's just never going to work particularly well. The geriatrician's job intrinsically becomes harder and harder as the patient gets older, because this damage that I'm talking about is continuing to accumulate and to impose more and more pressure on the creation and emergence and progression of these pathologies. So the geriatrician is fighting a losing battle. And for that reason, it's better than nothing, the geriatric approach, but it's not much better than nothing, and it never, ever, even in principle, will be much better than nothing. Someone didn't obey the instructions! Oh, it's for me. Oh, no, that's right. Right, so I'm not the first person to have observed that the geriatric approach is limited. This has been widely understood for a long time, and that is the reason why there exists this other thing called the gerontology approach. Gerontology approach has not actually led to anything very much yet in terms of postponement of age-related ill health. There are a couple of things, maybe, if you're arguably. But it might be getting there. The gerontology approach says, well, maybe prevention is better than cure. It often is. So maybe we can actually do better against the diseases of old age by intervening at an earlier stage in the chain of events, down here. Rather than trying to hit these pathologies, let's try instead to clean up metabolism and slow down the rate at which it creates these various types of damage in the first place. So the idea, of course, is that that would delay the age at which the damage reaches this pathogenic level of abundance. And that sounds pretty cool. It sounds like a much better idea. There's no intrinsic reason why that problem should get harder and harder as time goes on. Unfortunately, there is a big problem with the gerontology approach. Here it is. Metabolism is rather complicated. This is a simplified diagram of a small subset of what we know about how metabolism works. Okay, this is for those of you who don't know, this is a biochemical chart. Now, that's a bad problem. But actually, the real problem is not that. The real problem is that this is a simplified diagram of a small subset of what we know about how metabolism works. And as any biologist will freely tell you, the amount we know about how metabolism, about how our biology works, is absolutely dwarfed by the completely astronomical amount that we don't know about how metabolism works. Even ignoring all the stuff that we don't even know that we don't know. So, it's not doomed in principle. The gerontology approach is not doomed in principle. But in practice, it's an idea whose time has absolutely not come, not by a very long way. So we're just not going to make this stick anytime soon. So that's pretty bad news. But of course, if that were the end of the story, then I wouldn't be standing here. So the question then is, how can we do better? In order to explain how I think we can do better, I'm going to briefly use an analogy. I'm going to talk about cars. This is a car that's more than 50 years old. And that's, of course, pretty good for a car. Most cars, at least in the UK and the US, tend to fall over after about 15 years, and you junk them and get a new one. This one's lasted a lot longer. How? Why? The answer is obvious. It was built to last. It was built with, corrosion-resistant metal and really tough tires and all those good things. And I've seen some pretty old and pretty good, well-functioning cars in this country already as well, so I'm pretty impressed. But there is another way to make a car last a long time. This way of making a car last a long time is rather similar to how the human body lasts so much longer than the body of a dog or a mouse. We're just built better in the first place. We've got more comprehensive, more sophisticated anti-aging machinery built into us than they have. But here's the other way to make a car last a long time. This car was built in the same year as the one on the previous slide, and it's still doing fine. That's not because it was built to last. Rather, it's because it's been well maintained. It's got style, its owners have fallen in love with it, they've done a lot more maintenance than what the law requires them to do, and that's been enough to keep the car going, not just a little bit going, but going just as well as when it was first built. So this shows us that maintenance works. That if you can do a sufficiently comprehensive job of maintenance on a simple man-made machine, then you can extend its functioning, healthy lifespan far beyond its warranty period. So that tells us that in principle we might be able to do something with a very, very complicated other machine that wasn't man-made, namely the human body. And that is what I'm going to talk about for the rest of today. I'm going to call that the maintenance approach. You can call it the repair approach, if you like, the engineering approach. Essentially it said, let's not mess about trying to slow down this process where damage causes pathology. And let's also not try and slow down this process where metabolism causes damage. Instead, let's try and uncouple those two processes from each other. Let's separate them by going in and periodically repairing these various types of damage so that even though they're being created all the time, they do not reach this level of abundance that causes the pathology to happen. And I believe that that approach is vastly more promising than the other two approaches. Essentially, for a very obvious reason, it avoids the problems that I've already outlined with the other two approaches. On the one hand, it's sufficiently preemptive. We're not proposing to do something like this, which has this problem of this downward spiral of accumulating precursors, because this, by definition, doesn't have any accumulating precursors. This is the initial lifelong consequences of metabolism. But secondly, and perhaps even more importantly, the maintenance approach avoids the problem of the gerontology approach, because here what we're doing is, we're saying let's actually not try to slow down what happens here. Let's let metabolism create damage at the rate that it naturally does so. If we do that, then basically what we're saying is we don't need to know very much about how metabolism creates damage in the first place. All we really need to do is characterize what the damage is and then figure out ways to repair it. We're effectively sidestepping all of our profound ignorance about metabolism. And as engineers, I'm sure you appreciate that that is a pretty intelligent way to go about addressing a problem, a really hard technical problem. Trying to find ways to sidestep what you don't know about how the system works. But what about cryonics? Now, I was asked to talk, I don't work on cryonics, but Crenny, the main organizer of Techfest, asked me to say a few words about it, so I will. Some of you in the audience do know what cryonics is, I just discovered that. But for all of you who don't, let me explain. It is the idea of preserving a dead person very shortly after they became legally dead by taking them down to liquid nitrogen temperatures, by freezing them, taking them down to almost minus 200 degrees centigrade. The idea of doing this is that at such temperatures, the decay of the human body that, of course, obviously occurs at room temperature or even at, 0 degrees centigrade, is completely arrested. No decay happens. Even for thousands of years, nothing moves because the temperature is just too low. And the idea then is that by preserving someone in this way, we might be able to revive them again, to treat them from the thing that they legally died of, by using medicine that's not yet been developed, that's much more sophisticated than anything we have today. We essentially warm them up and apply this new medicine to them. The reason why this is not completely crazy is because legal death is not a biological phenomenon. Legal death is a sociological convenience because we just like to have people be either dead or not dead, and not somewhere in between. But from a biological point of view, what happens during death is a very gradual process. Essentially, when the heart stops, oxygen stops being supplied to all our tissues, especially our brain, and that causes a whole bunch of things to start going wrong quite rapidly, but not instantaneously. So the amount of damage that accumulates, even in an hour after the heart stops, is not really very much compared to the amount of damage that was already present in the brain before the heart stopped. And we know that this is true in practical terms because you can revive, very often, kids who've been unconscious and not breathing for an hour if they've, for example, fallen through ice on a frozen lake. This has happened a number of times. There are a number of perfectly good cases of this. And these kids just don't have any side effects at all. They're basically fine. So we know that the concept of this is not completely crazy. It's very difficult because, of course, if you actually freeze biological tissue, then there are problems caused by that process. But some of those problems have been very powerfully addressed already by research in this area, and other ones are moving forward fast. So I think cryonics is a very good bet. I don't want to end up being frozen anytime soon. I would like to carry on staying the way I am right now with my heart still beating. But if it's a choice between being frozen or being cremated or buried, then I'll take being frozen, because that will give me a chance of continuing my healthy life later on, after a bit of a gap. And I think that's perfectly fine. The reason it's relevant to what I'm talking about today is because the process of reviving someone in the future who has been cryopreserved is simply a natural extension of what I'm talking about today, of regenerative medicine and for the problems, the accumulating problems that people suffer in old age. Of course, there will be much more sophistication involved than there will be in the sort of things I'm going to be telling you about today, but that's just a difference of degree, it's not a difference in principle. So I think that it's entirely a plausible bet that by the time most of you die anyway, that cryopreservation will be sufficiently sophisticated to make it very likely that somewhere in the future we'll be able to bring you back. However, I think there's a fair chance that most of you won't have to worry about that, and in fact there's a little bit of a chance that even I won't have to worry about that, despite the fact that I'm twice as old as most of you. Because we're actually fairly close to developing technologies that ought to be able to make a decisive difference, in my view, to how long people can stay healthy and avoid any of the diseases and ill health of old age. I think that the therapies I'm describing here on this slide all have a good chance, at least a 50-50 chance, of being developed within the next 25 years. The big breakthrough that I made about a decade ago that's allowed all of this work to get off the ground was really just a conceptual breakthrough that came down to this list on the left here. This list is a classification of damage. So far, as you probably noticed, I've only spoken about this damage in very abstract theoretical terms. I haven't told you what it really is in concrete biological terms. So that's what I'm going to do right now. This, in my view, is a complete, exhaustive classification of all the types of damage that actually matter, that accumulate throughout life as intrinsic side effects of metabolism and eventually contribute to age-related ill health. There are three cellular ones, that top one and number 4 and number 7. Those are basically having too few cells because cells are dying, not being automatically replaced by the division of other cells, or having too many cells because cells are not dying when they're supposed to. There are various cases where that is important. Or having too many cells because cells are dividing when they're not supposed to. That, of course, is cancer. Then there are a couple of problems in the space between our cells, that's number 2 and 3 there, where we get either molecular garbage accumulating in the spaces, amyloid plaques in Alzheimer's disease is a good example of that. Or alternatively, the actual lattice of proteins that hold our tissues together, which is called the extracellular matrix, gets less elastic, and that makes it work less well, especially in the major arteries, causing high blood pressure, for example. The other two problems are inside the cell. First of all, there's this special part of the cell called the mitochondrion, which has its own DNA, and that DNA accumulates mutations, which seem to be bad for it. And secondly, there's, again, molecular garbage, junk inside cells this time. That turns out to be a harder problem to deal with than junk outside cells. So that's a pretty interesting classification. You may be thinking a couple of things. Number one, well, each of those categories is pretty broad, isn't it? Because, you can have a lot of examples of different things that count as cell loss, for example. And you're damn right, that's absolutely true. And the other problem you may have with this is, well, how do I know that this classification is exhaustive? Let me deal with that second one first. Good reason why we can think it's exhaustive is it's been the same list for nearly 30 years. That's a long time for people not to have come up with 8th and 9th things to add. Plus also, you can get this list just by analysing the body and asking where are the structures that are sufficiently long-lived to be able to accumulate damage throughout life. And you get pretty much this list that way too. The question of whether the classification is useful is a really important one. And the reason it's useful is because of the list on the right here. Yes, within each of these categories there are a lot of examples, lots of different tissues affected in different ways. But within each category, pretty much the same sort of therapy seems likely to work, with only relatively minor modifications depending on which example within the category you're looking at. So, stem cell therapy, you all know what stem cell therapy is. It's a big field, stem cell research, and the reason it's a big field is precisely because you need to do different things to different tissues if you want to fix them up and restore the cells that they've lost and not replaced on their own. But even though it's a big field, it's a field. It's an actual well-defined field, and that's because there's a great deal in common between different stem cell therapies, different prospective stem cell therapies. So it makes sense to have that as a category. And the same applies right the way down the list. So that's really why this classification is both useful and a source of considerable confidence that we will actually be able to achieve a very substantial increase in healthy human lifespan within the foreseeable future, within a time scale of a few decades. When I say substantial, this is what I mean. I call it robust human rejuvenation. I define that as adding 30 years of additional healthy life to people who get these therapies. But critically, the key point here is this healthy life will be added to people who are already in middle age. That's because these therapies, as I mentioned earlier, are ones that repair damage, that actually turn back the clock rather than simply slowing the clock down. So now, how close, why do I say we're so close to doing this? Well, first of all, in some cases, we're really close, a lot closer than a couple of decades. We've got clinical trials for stem cell therapies going on. We've got actually a case with regard to item 2 here, which is in phase 3 clinical trials. That's the last stage before regulatory approval in the USA. So that's pretty good news. We're really getting close to making these things work. Some of these were a lot less close, and the work that's going on is in typically only in cell culture or in mice, and that's the sort of stuff that that my foundation works on. We focus on the proof of concept work that allows people sufficient confidence to be able to actually get money from the government and so on. We try to get our money mainly from philanthropy to just get people excited about the possibilities, the long-term possibilities. I want to say a word about this one. This is one of the harder items on the list, but I want to show you how much progress is being made, and again, how widespread this work is. This is not just me and my foundation doing all of this stuff. There's a couple of figures from a paper that came out a few months ago in a very top journal, in Nature, and it was showing how if you could get rid of a particular type of what I'm calling death-resistant cell that accumulates to excessive numbers, you get an enormous benefit in terms of health. These mice have been engineered so that they accumulate a particularly large number of this particular type of cell, and this is one of those mice when it's maybe a month or so from dying. This is one of those mice when, a few months earlier than that, it was treated but with a trick that allowed us to eliminate all of those excessive death-resistant cells, and as you can see, it's looking much more robust. This is one of many different graphs in this paper showing changes in various aging parameters and the elimination of those changes if you did this therapy. So this just looks at actually the thickness of muscle fibers, but there's dozens of different things in this paper that they looked at. So this is pretty good news. It's totally mainstream, respectable science. It's published in the absolute top journal in the world, and it's happening now. So we are getting awfully close to being able to do these things. I'm going to spend a little bit more time now on something further down the list, this one here, which is really one of the flagship projects of SENS Foundation. This one's quite glamorous. I think you'll rather enjoy it. This is the sort of problem we're trying to solve. The number one cause of death in the Western world, and maybe also be true in India for all I know, is cardiovascular disease, atherosclerosis causing heart attacks and strokes. And cardiovascular disease starts with this phenomenon that I'm showing you here. It starts with perfectly healthy white blood cells infiltrating the walls of our major arteries to clear out detritus that has become stuck there in various little places called the arterial intima. And those white blood cells do their job perfectly fine for a long time, but they get poisoned by contaminants in that detritus that they are not enzymatically equipped to destroy. And they become a sort of undead white blood cell called a foam cell. That's one of these. This is the thing that goes wrong. There's a part of the cell called the lysosome, which you can think of as the garbage disposal machinery of last resort. The thing that gets rid of stuff that none of the other garbage disposal machinery in the cell can get rid of. And the lysosome gets poisoned by these contaminants that I mentioned. and it stops being able to do a lot of things that it used to be able to do quite well. So this is what you get, and it all becomes very chaotic very quickly. So how are we going to fix this? Well, essentially, what I have proposed, and what we're working on at SENS Foundation, is to use a technology that comes from a completely different area of biology, nothing medical at all. It comes from environmental decontamination. But many, many years ago, more than 50 years ago, it was suggested that we could find bacteria in the soil that would be able to destroy compounds that were polluting, things like TNT or dioxins or whatever. Turns out that's true. You can find such bacteria because these compounds are energy rich. If you're a bacterium and you can break them down, then you can live off them. So there's evolutionary pressure on bacteria to develop machinery to break these things down. So what I realized was that the compounds that cause these problems in the body, like atherosclerosis and also macular degeneration, the main cause of blindness in the elderly, and various other things, these compounds are also energy rich. So there should be bacteria that can break them down. In particular, there are probably bacteria in graveyards that can break them down, because graveyards are enriched in human remains. And it turns out that this is true, basically, that we are able to identify such things. Now, of course, the idea is not to then inject these bacteria into the body. That might be counterproductive. They might be quite toxic. But we should be able to find out how these bacteria are breaking down these substances, what genes and enzymes they are using. If we can do that, then we can add those genes and enzymes to our own cells and thereby augment our own cells' capacity to break things down. So the idea is just explained very simplistically and graphically here, that there's this natural process in the human body that turns young people into old people, and eventually into dead people. And then there's this completely different process that turns dead people into decomposed people, right? And that process is encoded not in the human body, but in the environment, in the bacteria and such like in the soil. So if we can figure out how that's happening, do standard cell biology, molecular biology, and then apply that knowledge to our own cells, this is my horrible cartoon of a neuron, then we can combat, then we can counteract the initial process that turned young people into old people in the first place. So yes, as I say, it does seem to be possible to do this. This is step one. We identify a whole bunch of bacteria and we grow them on the material that we'd like them to destroy. In this experiment we use this particular chemical, 7-ketocholesterol, which seems to be public enemy number one in atherosclerosis. And as you can see here, 5 of these strains of bacterium that we gave this stuff to couldn't do anything with it whatsoever, and so they just sat there. But the other 2 strains had a well of the time, and after only 10 days the material was entirely gone. You don't even need a microscope to see the results. So that's all very encouraging. Step 2, as I mentioned, is to find out how this is actually occurring, what enzymes are being used. This is one of the approaches that we have employed for that purpose. It's called mass spectrometry. You basically just identify the breakdown products that have been created as a result, as a side effect of the destruction of the target compound. And from that you can infer what the enzymatic reaction was, and then you can use bioinformatics to find candidate genes. We've been very successful with that method and other methods for identifying such genes. Then step 3 is, as I mentioned, to put those genes into our own cells. Of course, we start off by doing that in cell culture. That's not trivial, because, first of all, the bacterial cell is much simpler than a mammalian cell. So you've got to do a bunch of stuff to make sure that the enzyme goes to the right place. This is a little experiment showing that. This here is a stain for the right place, the lysosome. It shows up where the lysosomes are in cells. This here is a stain showing an engineered gene that we've been using for this purpose. And this is just an overlay showing that they're more or less the same place. So that's good news. We have succeeded in targeting our enzyme to the right location. Finally, we need to figure out whether it's actually working. There's many reasons why such an enzyme would be inactivated in the mammalian cell, for example, differences in pH. But it seems to be working. We're pretty happy about this. This is a very preliminary experiment. This is not published yet, unlike the other things earlier. So I don't want you to get too excited, but it's looking pretty good. Basically what this is showing is that if you give cells a completely humongous amount of 7-ketocholesterol, then they all die whether or not they've got this enzyme because they're just overwhelmed. But if you put more modest amounts of the toxic stuff in these cells, then the engineered gene really helps. If we basically the y-axis is just measure of how cells are surviving, how many cells are surviving. And the fact that this bar here is taller than the others says that if you've got cells with this gene in them, targeted in the right place and with the gene working, then they do better than if they don't have the gene at all, or if they have the gene that's not targeted to the right part of the cell, and so on, a couple of other different types of control. So that's all pretty heartening, pretty encouraging. Pretty happy about all that. Now, I've told you about steps 1, 2, 3, and 4 of this whole project. We know how to isolate strains of bacteria that do interesting things, work out how they do them, get our own cells to do them, and make sure that the thing actually works. But of course then, we've got to put these things into living organisms, into mice, and got to get them to work there. And that's going to take a little while. This is a non-trivial experiment. It's going to take us quite some time. And only then can we start moving on to clinical trials. So this is an ambitious project. And most people would say it's too ambitious for them. They'll work on something easier, something simpler. But, well, you heard this morning, or we heard hearing about electric bikes. You know, thinking big is a very, very useful thing to do. If you actually want to look back on your life 60 years from now and feel that you've done something, then start now. Start thinking big right now. Because people who think big are the ones who actually make a difference in the world. And there's nothing better in life than making a difference. So that's why we do what we do. We're interested in working on the things that are too hard for most people to have the guts to work on. And we know that if we do work on those, if nobody works on those, then in the long run, everybody suffers. It's very easy to think that what's worth working on is, for example, just helping the disadvantaged. And I'm all for helping the disadvantaged in the world. But if we only help the disadvantaged, then in the long run, everyone is disadvantaged. We have to push forward the leading edge of technology, including medical technology, just as much as pushing forward the trailing edge and helping people at the bottom of the ladder. So that's really the big reason why we work on these extremely ambitious experiments and why we try to get them to proof of concept so that other people will have the confidence to work on them too. Okay, so now for the last 10 minutes or so of my remarks, what I'm going to do is talk about the longer term. I've mentioned this up here, 30 years of additional life for middle-aged people. And that's pretty impressive. That's a lot more than we can do today with medicines that have so far been developed. But especially because you guys are mainly engineers and mathematicians and so on, I thought I would spend a little while talking about where I see this going more in the long run. Because there's quite a lot to say about this, and it's quite exciting. I've told you that slowing aging down by cleaning up metabolism is actually really, really difficult to do. Incredibly difficult. But even supposing I was wrong about that, supposing it were easy, is it actually the right way to be going anyway? Is it actually going to give much bang for the buck? Not really. If we think about it, then we can describe it in this very simple schematic way. The red line here I'm using to denote normal aging. Okay, so age on the x-axis, on the y-axis I've got reserve. That's simply the reciprocal of damage, the amount of additional damage that you can afford to accumulate before things start going wrong. So, of course, people start off at age 0 with not much damage, lots of reserve. Time goes on, aging happens, they accumulate damage, their reserve goes down. Eventually they hit this dotted line here I put in called the frailty threshold. That's when pathologies start to emerge, and then they haven't got long to go. So if we had a therapy that was able to halve the rate of accumulation of damage, then we'd have something like this. You'd start the therapy at some age, and the person would live an extended, healthy life. The other good news is that unhealthy life down here probably wouldn't be very extended, because when you've got these pathologies already emerging and spiraling out of control, exacerbating each other and so on, then therapies that work in the early part of life probably don't work very well anyway. So this looks pretty good. But the critical feature is you have to start rather early. If you start in middle age, then the person only gets a much smaller amount of additional healthy life. Bit of a shame, really. So actually, it would be much better to use these rejuvenation therapies, these repair therapies, even if there were not already this problem of technical difficulty of the retardation approach. step further with the retardation approach, though, we can say, well, okay, hang on. Supposing we start this therapy in middle age, but we carry on, while we're applying the therapies to people, we carry on trying to improve the therapy, to improve the effectiveness of the therapy. So here what I'm trying to show is the person starts doing the therapies here before they hit the frailty threshold. We've, again, doubled the efficiency of the therapy. So we've made the rate of accumulation of damage be only a quarter of the natural rate instead of half the natural rate. And of course then, you get an extra increment of healthy life before the person hits the threshold. But even then, it's still not as good as simply starting earlier, except that, starting earlier wasn't possible if the therapy hadn't been invented yet. So this is what we get if we look at an equally effective, an equal quality rejuvenation approach, repair approach. We take someone in middle age, and instead of getting only this pathetic little amount of extra life, we can apply this therapy. Again, I'm saying it's a 50% effective therapy, so it affects roughly half the damage. We can apply it repeatedly, so we end up getting all of this extra life. Of course, every time we apply the therapy, it is less effective because the difficult damage that the therapy doesn't work on is continuing to accumulate. So eventually the difficult damage on its own is going to be enough to knock our hero over the frailty threshold, however thoroughly and frequently we're applying this therapy. But it's still one hell of a lot better than the retardation therapy. That's pretty good news. And that's why I think that these rejuvenation therapies have a very good chance of giving as much as 30 years of extra life to people who are in middle age before we start, which is far, far more than any therapy based on slowing aging down could do. But that's not the end of the story. I spoke a moment ago about the fact that if we continue to improve the therapies, these retardation therapies, we can get an extra increment of life. Why don't we apply that same additional feature to rejuvenation therapy and see what we get? The answer is, this is what we get. Supposing we've taken this person who's been rejuvenated the first time, and we then apply the rejuvenation therapies again, but just as down here, we have made progress and we have doubled the efficacy of the therapy. In other words, now, rather than just fixing half the damage, it also fixes half of the remaining half that we couldn't fix beforehand. Now, let's think about whether that's reasonable. That's like, maybe there's 10 or 15 years, maybe 20 years between the first and second applications of these therapies. So, improving something by a factor of 2 in that time doesn't sound all that unreasonable, does it? And so this person would be up here. And as you can see, not only would they be more rejuvenated than if they got the old therapies, they're actually more rejuvenated than what they were when they got these old therapies the first time, even though they were chronologically much younger at that point. And if we apply that concept repeatedly, then we get this. And as you can see, this line here has a profound qualitative difference from all the other lines. In other words, it never hits the frailty threshold. So that's why we can actually talk not about 30 years, not even about 100 years, but about indefinite maintenance of true youthfulness, of staying exactly how you are today, just like young adults, however long you live, however long it is until you get hit by a truck. Oh, and incidentally, why don't any of you bloody wear seatbelts? I don't get it. I've been driving around this place for the past 24 hours and none of you wear seatbelts. What? Damn. Alright, enough about seatbelts. Right, so we really can talk about indefinite postponement of age-related ill health. And that's why. Now, of course, the key point here, you've got to actually improve the therapies fast enough to stay one step ahead of the problem, to have the general long-term trend be upwards rather than downwards. And that's such an important point that I gave it a name. This is the minimum rate of progress. I call it longevity escape velocity. It's the minimum rate at which we need to improve these therapies in order to stay one step ahead of the problem and not just have eventual frailty happen anyway. So it's quite nice to know whether we can in fact be confident that we will be able to achieve longevity escape velocity. And in order to address that, sometimes I just talk about other technologies. I say, well, I mean, look at what we've done in, like, powered flight, for example. We double the functionality of airplanes in much shorter time than the sort of time we were talking about there. But let's do something more direct. Let's do a computer simulation. This is what I did a few years ago. Here's my definition of aging that I've been using all day. So we did a simulation of that in such a way that we would be able to say, well, okay, now what would happen if we applied these interventions, developed and improved on some schedule or other. So here's basically what we got. This is all published. Obviously, I can send reprints to anyone who wants them. But this is what we get. Now, these are survival curves. A survival curve is simply a graph showing what proportion of an initial population is still alive at any given age. So the black line here is not a simulation. The black line is real, actual data from America, showing the survival of, I think it was people 10 years ago. So of course everyone's by definition alive at age 0. Hardly anybody dies until age 50 or 60, then they start dropping like flies, and hardly any of them get beyond 100. All that. Now, the blue line, the dark blue line here, is a simulation of a group of people who have the same intrinsic risk of death at any given age that the people in the black line have. But these people are getting these rejuvenation therapies from only the age of 80. Okay? Now, a couple of things I want to say about that. First of all, by age 80, of course, half of the typical Western population is dead. So that's why the two lines are coincident. But then after that, as you see, there's not much benefit. Why not? Because these people are already not doing very well. And this, again, of course, brings me back to the critical point that this is all about health. This is all about keeping people in a good state of health, not about keeping them alive in a poor state of health. If you're in a poor state of health, you have a high risk of death each year. That's just how it is. So the reason why you don't get much benefit here is because these therapies just didn't get to be good enough, quickly enough, to bring these people back from the brink. They all just ended up keeling over anyway after not much additional time because they weren't in a good enough state to benefit. But now, let's look at this line, this grey blue line. This one is the same simulation, except that in this case, the therapies are initiated 10 years earlier, when starting from the age of 70. And as you can see, it's very much the same story at first, but then people who survive long enough start really being rejuvenated. The therapies start getting the upper hand. And you end up with 10 or 15% of these people having the risk of death from any kind of age-related cause completely eliminated permanently. These graphs do not depict death from cause related to aging. So, this is longevity escape velocity. And the brown line here is what happens if the therapy was started at the age of 60, but nearly half of people get to that sort of point. But here's the real kicker from this graph. Here's the thing I really want you to take home from it. This up here. In this particular simulation, I was just ludicrously, insanely over-pessimistic about the rate at which we would make progress on these therapies. I said we'll double the rate of the therapy's efficacy only every 42 years. Now, I mentioned powered flight a minute ago. Powered flight, right? 42 years is the time between the year that Lindbergh flew across the Atlantic, the first solo flight across the Atlantic, and the first time that Concorde flew across the Atlantic. So how crazy is that we would only get a doubling of progress in 42 years? Especially since we're now obviously progress is faster in general because it's later. So, this really shows very directly and extremely compellingly that once we get anywhere near to this thing that I'm calling robust human rejuvenation, getting this 30 years of extra life, we will be at longevity escape velocity and we will have done the hard part, so to speak. That brings us to conclusions like this. We do not know how old the first 150-year-old is today. The world record lifespan, the world record verified lifespan, record is 122. So we won't get people to 150 without creating robust human rejuvenation. And I think we've got a 50-50 chance of getting to that point, getting that technology in place within 25 years or so. But I want you all to know that just like any other long-term prediction in technology, that is an extremely speculative one. In other words, there's at least a 10% chance that we won't get there for 100 years. That doesn't bother me. A 50% chance is quite enough to be worth fighting for, but it's very speculative. We do not know how old that person is yet. But we do know, from what I've just told you, that by the time we get there, we will have done the hard part, which leads us to conclusions like this. The first 1,000-year-old is almost certainly only 10 or 15 years younger, if that, than the first 150-year-old. That is a pretty dramatic conclusion. 1,000, by the way, is not taken out of the air. That's the sort of age that anyone in the West would get to already today if aging didn't exist. It's just, what your half-life would be if you had the same risk of death at any age that you had in your mid-20s. So, this is a pretty dramatic conclusion, but it's inescapable. It doesn't matter how counterintuitive it may be, it's inescapable. Now, most people, when I talk about this, especially most non-scientists, they tend to say, oh dear, this sounds like a terrible thing, because they've been conditioned to feel, to make their peace with aging, to feel that aging is natural and that we shouldn't mess with it. But that's nonsense. If we approve of medicine in general, then we are approving of keeping people alive when they wouldn't otherwise be alive, keeping people healthy when they wouldn't otherwise be healthy, and keeping them alive as a side effect. And this is absolutely no different. The fact that these therapies are for people who happen to have been born a long time ago makes them no different from anything else. This is all about health. And I mean complete health. I don't just mean being healthy for your age. I mean being able to keep up with your granddaughter on the dance floor. Look, I really mean, exactly this. But even when I give lectures like this, people will very often stand up at the end and they'll say how awful it would be to be old all that time. Hello, Tommy, I've been spending the last hour saying that it was about being young all the time. But it really happens. It really happens. People do that. So they say, well, okay, even if I was young, I wouldn't want to live all that time. It would be really boring, or, what would I do? Honestly. I mean, I've got at least 1,000 years of backlog of things I haven't had time to do already. But also, it's not about the longevity, it's about keeping healthy. That's what it's all about. People also come up with all manner of sociological objections, like, where would we put all the people, or wouldn't dictators live forever, and so on. I mean, how much imagination do you need to have, really? All of these things ultimately come down to presuming that the very slow, mentally, changes that would occur as a result of these technologies will occur in the absence of any other changes in society or in technology. For example, people worry about overpopulation. There's nothing wrong with having 7 billion people on the planet. What's wrong is having 7 billion people, each of whom has a significant ecological footprint. So, if, for example, we succeed in the next few decades in actually finally inventing nuclear fusion and therefore end up essentially dramatically reducing fossil fuel utilization, then, lo and behold, it won't be such a problem having 7 billion people on the planet, and so on. So it's crazy. This is the one that annoys me the most, by the way. I mean, it really does. It just gets me down. The idea that it only matters if it's going to be in time for you. I mean, people honestly say this to me all the time, especially the wealthy ones that I try to extract money from. But what it really shows is that these people are not actually thinking about the question. I mean, they wouldn't dream of saying something so selfish in any other context. But people say it because they really just don't actually believe a word that I said, even though they can't, about the feasibility of all this, even though they can't actually see anything wrong with my argument. So they're willing to say things that, that just wouldn't make any sense in any other context. So, I mean, a reminder, now, of course, I haven't gone into much detail today, but a few years ago I wrote a book which goes into excruciating detail about all of these therapies that we're developing and why. And I very much hope that some of you will get hold of it and have a look at more of this. It doesn't require any prior technical knowledge. It's written without any jargon, but it is very detailed. And I'll stop there, and I'd like to take questions for 5 minutes. Okay. Lights? Do we have any more lights? Oh, there's a question up there. I can't hear it. There's a roving microphone, isn't there? There's a mic. Yeah, wait for the microphone, so I can't hear anything and not anyone else. You got the microphone? Too bad they can't find it. Okay, shout. Okay, the question is, do antioxidants really work? And the answer is basically no. And there's a very simple reason for that. Free radicals, which are the toxic molecules that antioxidants try to eliminate, are molecules that evolution has had to live with for a very, very long time, ever since breathing was invented about 2 billion years ago. Now, that means that evolution, as it tends to do, has made the best of a bad situation and found uses for free radicals. They are used very widely in cells as signaling molecules and so on. So what actually happens when we overload our system with dietary antioxidants that try to reduce the level of free radicals is the body just compensates and down dials its own antioxidant machinery so as to leave everything more or less the same. This is basically the deal with trying to do simple things to aging. Either the body will just, you'll do more harm than good because of something you didn't understand, or else the body will just laugh in your face and get on with what it was doing anyway. So that's the basic answer.
Is there a gene responsible for aging which can be altered?
Alright, so is there a gene responsible for aging? No, and for essentially the same reason as for my previous answer. There's no point in having a gene for aging, or any genetic program for aging in our genes. The only way that there could be any reason to have such machinery would be if it were in some sense evolutionarily a good thing for older individuals to be eliminated from the population. But it can't be evolutionarily a good thing because individuals in the wild are eliminated from the population at any age at a very high rate. So you hardly see any instances of actually old organisms in the wild anyway, whether it's humans or mammals or plants even. They just don't get that. They just don't live long enough to get that way. So there would be no, even if we had magically acquired such machinery, there would be no natural selection to maintain it. So it would mutate into oblivion rather quickly. Sure. Yeah, absolutely. So I've been asked to wind up because we're running late, but obviously my email address is right here, so anyone who has any other questions is welcome to do that. Also, I will be around for the rest of the afternoon if anyone wants to catch me. Thanks very much.
Thank you, sir.